Hello everyone, welcome to our presentation about music ensemble separation, where we use a synthesized dataset EnsembleSet to train source separation models that are able to separate real mixtures of two monophonic musical sources regardless of their instrument type. Music source separation research has seen great advances in recent years. We have achieved great results in separating vocals, bass, and drums from songs. These methods work very well and generalize respectably in the real-world scenarios, but this research has been largely focused on the stems shown here, that is vocal space and drums. This has been especially aided by the very popular MuseDB dataset, which is one of the largest and easy-to-use music separation datasets available. One of the popular expectations from source separation is the desire to pick out any instrument present in a recording, regardless of the constituents of the mixture. This is particularly challenging due to multiple reasons. Firstly, it is the actual signal-to-noise ratio of the target instrument in the mixture. If the target has a very poor signal-to-noise ratio to begin with, there isn't a great deal you can achieve with masking. Secondly, if the target instrument is one of the harmonic instruments of the song, it is even more difficult to separate as harmonies typically result in very high spectral overlap and similar F0 ranges. Moreover, if you have two identical instruments, the class-based separation paradigm doesn't really solve that. And then finally, MuseDB is a very structured dataset where each song will have all the constituent targets present throughout. For other instruments, we lack such large amounts of data. My research has been focused on trying to address the last couple of these issues. Our task tackles the problem of separating chamber ensemble instruments from a monaural recording. In our problem definition for these experiments, we have two instruments that are present at equal loudness in a mono recording. The instruments are playing in harmony, thus resulting in significant spectral overlap. Moreover, the instruments present in the mixture don't need to be distinct. They can be two of the same instrument as well. There is a challenge to gather clean real-world data for this task, as unlike pop recordings where each performer is recorded in a separate take, chamber ensembles typically require to be able to hear each other while recording, to be able to adapt to the other performers and blend in to create a coherent sonic texture. As a result, even professional studio recordings would have bleed present in their stems, thus making it very difficult to obtain clean training data for this. Thus, in our work, we utilize a high-quality synthesized dataset EnsembleSet to train our models. We train our models such that the same model is able to separate all kinds of instruments from a mixture as long as they are monophonic. We test our models with real-world recordings of ensembles from URMP dataset. We see that our model is in fact able to generalize well to unseen real-world recordings even when the model is trained only on synthesized data. We further try to improve our model's performance by taking our pre-trained models from EnsembleSet and fine-tune it with limited amounts of target domain data. We find that pre-training using EnsembleSet not only improves chamber ensemble separation, but also improves vocal harmony separation tasks. Analysis of the performance of these models show that these models perform in a timbre-agnostic fashion, where they are also able to separate unseen instruments. Meanwhile, the performance shows high degree of variance that is directly correlated to the musical complexity of these mixtures. To train these models, we use time domain source separation networks based on TASNets together with permutation invariant training. Using permutation invariant training allows us to train our model in an instrument-agnostic fashion. We just present the model with mixtures of two musical sources for all possible combinations available in the training dataset. Then during training, you basically compute the loss for each possible output target source assignment and then choose the assignment with the minimum loss and then backpropagate. EnsembleSet consists of 80 chamber ensemble pieces rendered through the Spitfire BBC Symphony Orchestra sample library, which allows rendering each instrument without bleed in 20 different microphone configurations. The dataset has a total of 6 hours and 10 minutes of chamber ensemble pieces, with around 500 hours of total audio data. We use the multi-mic renders available in this dataset as data augmentation during training by randomly choosing one of the 20 mic positions for each training iteration. We observed that this multi-mic augmentation significantly improves the model's performance, and in fact, our time domain DPTNet model depends on this for cross-dataset generalizability. However, we test the same on complex domain STFT-based model DCUNet, and we find that our multi-mic augmentation doesn't improve the performance for this complex domain model at all. Majority of our training dataset consisted of string ensembles and had very limited amounts of other chamber ensemble instruments. In the figure on the left here, you can see that it has many hours of string quartets, but the other wind and brass instruments only have a few minutes of data. However, on the right, we see quite consistent instrument-wise performance of our model that is trained only using EnsembleSet and tested using real-world mixtures from URMP. You can also see that most dominant instruments in the training set, that are the string instruments, surprisingly perform the poorest on average. Since we see that horns perform the best across all instruments, we trained another model by removing all examples of French horn from our training set, and we observed that still French horns perform the best. Moreover, fine-tuning the model with a 4-minute string quartet piece seems to improve the performance across all instruments. This was the first sign for us that suggested that the timbre of instruments did not really influence the separation capability of our model significantly. Based on this, we tried to use this pre-trained EnsembleSet model and fine-tuned it to be able to perform vocal harmony separation. This time, however, the amount of data required was a bit more, around 20 minutes, but we still find that surprisingly, pre-training using chamber ensemble instruments also seems to benefit the task of vocal harmony separation. Here is an example from our experiments. First, we hear a two-source vocal harmony mixture of two male singers.
Ship is sailing o'er the sea, the rolling rest.
This is the separated output from our fine-tuned DPT-net model.
Ship is sailing o'er the sea, the rolling restless sea.
Now we hear the ground truth.
Ship is sailing o'er the sea,
To understand the behavior of these models, we undertake a deeper analysis of the impact of different musical contexts present in the mixtures on our model's separation performance. We observe that the mixtures of identical instruments are separated almost as well as mixtures of distinct timbres. More importantly, we observe a significant 5 dB drop in performance if the sources have a pitch overlap at any point within the 3-second input window. Also, we see that there are quite a few outliers for the non-overlap scenarios, so we try another condition which may explain those scenarios. Now we instead check for pitch crossovers, that is, if the two instruments' pitch trajectories cross over each other at any point during the mixture. We again see a similar performance drop in the average separation performance of our models in these scenarios. Moreover, again as before, the influence of the timbres present in the mixture seem to be minimal. Analyzing 40 of the worst performing examples from URMP dataset with less than 0 dB output SDR, we found that 35 of these examples could be classified as pitch overlaps or pitch crossovers. Manual analysis of these scenarios reveals that the model suffers from two unique failure modes in these scenarios. Firstly, unison seem to affect the separation quality of the entire input frame. Not only does the section where the unison exists fails, the separation around the unison also has some artifacts. But if you notice in these spectrograms, the separation before and after the unison also has significant bleed. However, in the pitch crossover scenarios, we find that the perceptual quality of these separated outputs is in fact quite good, even though the output SI-SDR is very low. We find that in these scenarios with pitch crossovers between silences, the output target assignment is swapped. This, especially in the context of mixtures of identical instruments, could be considered as a false negative, as the melody lines of two identical sources may be confused even by a human, especially given the context of only 3 seconds. Here is an example of such a mixture. And now we hear the two separated outputs of this. Thus, in conclusion, we find that using a permutation invariant training objective, we can train source separation models that are timbre agnostic. Moreover, using such a method, we can also separate two identical sources. However, the performance of these models seems to be quite sensitive to specific music scenarios. In the context of unisons, the source separation problem becomes a timbre or chorus disentanglement problem, which our model struggles to perform at. However, in the context of pitch crossovers, our model suffers from source confusion, although the assignment of such errors could be fixed at post-processing as the separated outputs are still quite clean. We hope you found our work interesting, and please feel free to get in touch with us if you have any questions. Thank you.